Hello and welcome to this tutorial where we will learn to make a D flip-flop and then we will simulate it. So in order to get a clear understanding of what we are going to learn today, it is important that you go through my previous lecture where I explain how we can make sequential circuits using Verilog HDL, which basically involves the use of always block. But even if you have not gone through it, you'll still get what is going on in this tutorial. So let's begin with making a new project. So click on this new project and let's name it flip flop, and then click next. So here you need to select the desired directory where you want to store your project, then click next. Select the required parameters, so you could select the type of FPGA and the simulator, and then you can click next and then finish. Right, so once you have made this project, so here you can add files to this project by right clicking and then selecting Verilog module and then naming your module. So let's call it D flip flop DFF. Click next, next, and finish. Right, so here we are going to write our Verilog code to implement D flip flop. So as we know, using behavioral modeling, we specify the behavior of the logical circuit instead of making the logical circuit itself using AND or other logical gate commands. So we are going to use that behavioral modeling here. So first we need to specify the inputs and outputs. So a D flip flop has an output, we call it Q, an input that we call D, and a clock. Right. Okay, now we specify that D and CLK are inputs and um, output is Q. Right, so since we are going to use behavioral modeling, so we know that in behavioral modeling we define the output as reg type because we need to change the value of output during the execution of the always block. So the reg data type allows us to change the value during the execution, right? So now you select the always block, give it the condition for execution. So it is important that you know that in sequential circuits, although we have used this always block in combinational circuits where we used all the inputs as condition for execution, but in sequential circuits you are only going to use this clock as a condition for execution. Well, we also have another condition, but we will go to go to that later. But initially you need to just specify this CLK, and in clock we have both positive edge and negative edge, so you need to specify on which edge of the clock you want to execute your flip-flop. So you need to write this pos edge keyword. So this pos edge keyword specifies that this always block should be executed on the positive edge of the clock. So we have named our clock as CLK, as you can see here, right? So we have named our clock as CLK, and now we are specifying that this always block where we are going to specify the behavior of our flip-flop, it should run on the positive edge of the clock, right? So once you have done this, now you write begin. So this is this begin specifies the start of the block, and end specifies the end, right? So in D flip flop, so D flip flop is basically a transparent flip flop. So whatever is on the input will go to the output on the next clock. So in this case, we have specified that the execution should happen on positive edge. So it means now, so whenever there is a positive edge, the input should go to the output. So it's a transparent latch, so we need to only write this statement to implement this. So that's it, right? So this is a D flip-flop, and we save this, and then we click on simulation, click on the D flip-flop, and then run its behavioral check, and there are no errors. So now let's make its test bench. So add new source, Verilog test fixture. Let's call it tb underscore dff. Next, next, and then finish. Right. So here we have declared the inputs as reg type. Again, this is because we want to change the inputs during the execution of test bench. So, and this is where we have called our module, and so here we are going to specify the input combination. So so we specify clock to be 1, and then we copy this D, and we make it 1, and then we again give some delay, and then we make this D is equal to 0. Right, so you could give whatever combination you want to give to D. So there it is. Now you need to specify the clock. So we have already defined the CLK variable, input variable, as 1. So now we need to specify the clock. So let's write this always command. So, and then you just need to write this, that CLK is equal to not of CLK, but it should happen with a delay of 10 nanoseconds, right? So what is happening here? So this is how, this is where you this is how you generate a clock, right? So this always block, because you have not specified any condition for its execution, now this is going to run indefinitely. So it is like an infinite loop that is running. After the delay of 10 nanoseconds, what it will do, it will reverse the uh, the the value of CLK. Initially, as we have specified here, CLK is 1, but when CLK, so when after the delay of 10 nanoseconds, CLK will be 0, and then after the delay of 10 further nanoseconds, CLK will now convert to from 0 to 1, and it will keep on flipping every time this always block runs after the delay of 10 nanoseconds, right? So let's simulate this, and so here we are. So as you can see, um, so this is the clock that we generated. So it is, as you can see, it is going from 0 to 1 every 10 nanoseconds. So the clock cycle of this clock is 20 nanoseconds, right? So each so 10 nanoseconds for 0 and 10 nanoseconds for 1, right? So as you can see here, so for first 100 nanoseconds, input D is 0. So as you can see, the output is also 0. But as you can see, this 100 nanosecond, after this 100 nanoseconds, as input changes to 1, output also changes to 1 on this particular positive edge. And similarly, when input changes to 0, as you can see, output also changes to 0. So this is how, this is what um, a D flip-flop, this is how D flip-flop works. So now, so there is one thing missing, that we have not yet included this reset, that basically specifies the condition to reset the flip-flop. So we need to add another input, RST, and here again we do the same. And so in here we specify that always block should also be executed whenever there is a change in reset. And again we specify that the change should be on the positive edge, or the execution should happen on the positive edge of the reset input. So here you need to specify that if RST is 1, the output should be 0. So when reset is 1, the flip-flop should reset. So this means Q should be equals to 0 when RST is 1, and else Q should be equal to T, right? So there we are. Right. So this is how we incorporate the reset conditions. So we save this. Let's run its behavioral check, and then we need to go to the test bench. So here we have added an extra input, so we need to add this RST to this test bench, and here also we need to do the same. And initially let's say RST is also 1, right? So we want to keep our flip-flop at reset initially, but when after 100 nanoseconds, let's say we say that RST is equal to 0. So now let's save this and run its behavioral check. Again, run the behavioral check of the input file. Click rerun all, and then rerun the simulation. So here we are, and click on this fit to screen button. As you can see, this is the reset. So as you can see, until the reset is 1, the flip-flop is at reset, but when reset is 0, now the flip-flop is working in its traditional way.